Hey, good evening, guys. We're going to be talking about Lab 9. This is the detailed walkthrough on Lab 9, and hopefully I can get that shared with you. I apologize. I thought we were sharing already. Apparently not. So sorry. Technical difficulties, of course. If it can happen, it will happen. Okay. Come on, work with me. Oh, yes. Awesome. So here we go. So I am looking at the lab summary that exists, and we're going to be looking at experiment 9, as I said. This is based on what's in the lab manual, which is the reaction between Mg solid and HCl, going to MgCl2 plus H2 gas. And every one of the things that we're going to be doing today is based on that experiment. So things that we're going to change are factors that may affect our reaction rates. So concentrations, temperatures, and the diameter of the coil. So what happens is we have a thin strip of magnesium that we use in the laboratory. We take a very long piece of it and take the weight of that really long piece. And that's because we can't measure an accurate weight on a 5 centimeter strip, which is what they ask us to cut most of these into. So we have to get a weight per distance for that whole thing. So that's why it's asking what's the magnesium Roman, the mass, and length. So we'll talk about that, and I'll talk about where that data is. And that's how we're going to do that. We have our concentrations. There are 4 concentrations we're going to look at. There are 4 temperatures that you want to be looking at, and then there are 4 diameters that we're going to want to look at. And so we want to make sure that we're looking at those things appropriately. Now, there is an Excel spreadsheet for this as well. Actually, where is my Excel spreadsheet for this? Let's see if I can find it. Okay, I do have it. Awesome. Because I should have everything. But what you'll see when you come into this is that there's going to be a place to put in your temperature data, your diameter data, and your concentration data. So, and that will give you all of the things that you're looking for. You'll get a plot of concentration versus rate, temperature versus rate, and diameter versus rate, and you'll be asked to comment on those. So there will be that. Okay, so when we look at this particular set of data, the first thing they're asking for is calculate the volume of the 3 molar HCl and the volume of water to prepare the required concentrations. So if it's a 3 molar HCl, we don't need to dilute that. And so we wanted to have, and my lab notebook says 20 mils. So we have no water that we're adding to that one, and 20 milliliters of this is what we're using because, again, that one is not diluted for the 3 mil or 3 molar. We are going to have to dilute for the 2 molar, however. So if I want my M2 to equal 2.0 molar and my M1 equals 3.0 molar, and my volume that I want of that solution is V2 equals 20 milliliters, then I should be able to calculate the volume of the first one. So V1 is equal to M2 V2 over V1. And I'll let you plug that in and do that calculation. This standard calculation we've been doing this whole time. So you'll get one of those for concentration 2.0, 1.5, and 0.8. Okay. And as we look at our, nope, it's not that one. It's here. So there is data that's been uploaded to D2L. You'll find this in the D2L shell, and I will show you where that is. Just in case you're not aware. So going into your shell, going to Sorry, my thing's in the way. Content. We are under, this one is reaction rates. So this should be exam 2, reaction rates, and kinetics, which is experiment 9. And then we have our factors affecting the rates. This is the PDF for that. This is the checklist for it. Here's my, the data is right here. So it's the third one down, that data. And you're looking at exactly what I'm looking at over here. So that's where that is, just in case you couldn't find it. So here's my data. And what you'll see is that we have the length of each piece of magnesium ribbon and the mass of each piece of magnesium ribbon. So they've calculated that for you. What that means is that this calculation right here is not required, okay, because that data is already present for you. So we have a mass for each of these pieces that goes in there. You can look at the length of each piece and the mass here 0.02, and the length 5 centimeters, and that will give you the calculation that you need to be able to do that. But there's that. So for each of these first few, this tells us that we want to be using 5 centimeters for each piece. So this should be 5, 5, 5, and 5. Now you can assume that this was exactly 5, that's what they did. That is not really what we see in the laboratory, but we can assume that that is what they did there. So you can fill that in as 5 for each of those. And then you're going to be measuring a time. So how long does that reaction take for each of those concentrations? And somewhere I have my data back. So the reaction rate is going to be the change in concentration over the change in time. Okay. And the way that they want you to calculate that, if you come down here and look, mass and length of the original piece, calculate the mass per length gram per centimeter ratio. With the mass per length ratio and the measured lengths of magnesium, calculate the mass of each piece. With mass of magnesium used and the time for the reaction to take place, calculate the rate of each reaction for each acid concentration in grams per second. So again, we're going to assume that this is 5 centimeters, okay? And we're supposed to calculate a gram per centimeter ratio. And so my grams is 0.02 grams, and it's 5 centimeters. So that's going to give me 0.0225, which is 0.004 grams per centimeter. Okay. Since I know it's a 5 centimeter piece, times that 0.004 grams per centimeter, that means that the mass of each of those pieces.
Hey lady, you gotta read your text message. I can't do it.
Is going to be 0.02, and I'm sorry, I thought I had turned the sound down on that. I'm really sorry. And so that's 0.02, again, in terms of grams. So that's my grams. Yay, I just went in a big circle, didn't I? Awesome. And then we're going to divide that by the number of seconds that it took for this particular reaction to happen. And you'll see that the reaction rate, the time is given here in seconds. So for concentration 3, the time in seconds was 6 seconds. For concentration 2, it was 13. For concentration 3 or 1.5, it was 27. And for concentration 0.8, we have 77. Okay. So you'll need to fill in all of that data. We'll do the same for our temperatures. Okay. And the temperatures that we're aiming for So room temperature, so roughly 20 degrees C, we will have 15 degrees C, a 35 degrees C, and then our 45 degrees C. And then we also have our room temperature. I'm hoping that there's an actual value that's listed here. Temperature is listed as 20, so 20 degrees C. And they're not in order. Whether you do them in order is entirely up to you. It really doesn't matter how you decide to do them. The time for each of these temperatures, so the 15 degrees is 27 seconds, the 35 degrees is 16 seconds, the 45 degrees is 14 seconds, and the 20 degrees is 23 seconds. And of course, all of these are still supposed to be 5 centimeter samples. So that's the data that we should be filling in there. When we look at our surface area, what we're doing with our surface area is that this magnesium strip that we have, we're rolling it up into coils. So one of the coils we make very, very big. One of them we make smaller, and then really, really tiny. And the reason that we do that is that the tighter that we coil that thing, the less surface area is available for that reaction. Okay, so surface area is important when we talk about solids, because if I don't have as much surface area exposed, I have less places that I can have a reaction on that material. So here we're using 10 centimeters. So each piece here is going to be 10. And we're going to be looking at, we want to measure the diameter. Okay, so let's see if that's in our data. And we have a diameter that's listed here. Diameter in centimeters is 2.9, 2.2, 1.2, and 0.8. And of course, what we're measuring is that piece that we've got coiled like this, we're measuring the distance across that piece. So that's what we're measuring there. And those are the diameters that we're looking at. We have 34 seconds for this one, 32 seconds here, 120 seconds here, and 226 seconds there. So that's all of your raw data that needs to be put in there. I haven't finished these calculations for you. You get to do that. But that's the raw data that you get from this data, the stuff that was provided to you. Okay, so that's your pre-lab stuff. Again, you need to finish this table right here. When we scroll down and look at our next page in this, we're looking for our objective. Again, your objective would be found on your first page here, which, if I'm not mistaken, is 53. The balanced reaction is on page 53. Enter your data into the Excel worksheet. So again, we're going to be looking to put that data, temperature, the centimeters, and the time, diameter, centimeters, and time, and then concentration, centimeters, and time. Okay, so that's what we're looking at there. This ends up being the calculation for the mass per centimeter. And of course, this for you guys was 0.02. So that changes your numbers a little bit. All right. So make sure that you've got that fixed in your spreadsheets. Make sure all of this data matches what you were using. All right. So that's what we have for that. Okay. So that goes in there, and that's number 3. So this is your Excel. So if you don't turn in your Excel, that's a problem, and it is a 20-point question for that. You're supposed to show the mass of the strip of magnesium used for the first trial, and then calculate, and that is, again, this calculation that we did previously. So looking right, so right here. So that calculation. So now that we know exactly what the mass per gram per centimeter times the 5 centimeters, then we get that 0.02. Okay, and that's in grams. So that's the calculation you should be showing there. I think that's 4A. Yes, 4A. And for 4B, we're going to calculate the rate for the 3 centimeter HCl trial. So again, what you want here is grams per second. And so if we look at the data that we have for that 3 molar, we have 6 seconds and it's 5 centimeters, which of course is 0.02002 grams. So this is 0.02 grams in 6 seconds, and I will let you calculate what that value is. So that's what you need to be showing there. For your discussion and reflection, we want you to look at the 3 graphs. And so once you've filled all of your data in for these, you have a graph here for concentration, one for temperature, and one for diameter. We want to know how is each of the properties related to this. So is it a direct relationship? As concentration goes up, the rate goes up? Is it an inverse relationship? So as concentration goes up, the rate goes down? Or is it an indirect? There's nothing relatable between them. Or is it exponential? So as I change this concentration, does it go up by a factor of 2? So does it keep getting bigger or smaller as we do that? So exponential. Okay. And you're going to want to do that for the concentration, the temperature, and the time. Okay. Your data will not fit particularly well, but that is something that we're looking at. Of course, you want to be looking at the actual raw data.
You gotta read your text message. I can't do it.
Rather than the line of best fit, because it may be that your data is not a real line, but I don't see anything here that looks like it would be anything else. So you should be fine there, just a hint, but let's make sure that that's what you're actually doing. You need to provide for us which factors seem to impact the rate most significantly. And that's up to you. You have to make that call yourself. And how you decide to make that call is what you need to explain. Okay. And you need to explain it in context of the collision theory. So remember, we said that there are 3 things that affect the rate that we talk about. One is, did they collide? Did they collide with the correct orientation? And did they collide with the correct amount of energy? Okay. So our expectation is that higher concentration would give us more reactions because we have more of these things that can hit each other. So greater collisions because of higher concentrations. We would expect greater collisions with higher temperatures because everything moves faster. And of course, as our diameter gets bigger, we give it more surface area. So the expectation is that that would be faster. Okay. Explaining outliers in your experimental data. Okay. So there's that. That's your summary. As far as your post-lab goes, what was the limiting reagent for each of these trials? You have 2 things that we're talking about. One is HCl, one is the Mg. Which one is your limiting reagent? And a big clue, how would you know if the reaction was done? So if you've taken a piece of metal and you've dropped it into the acid, what would you expect to see? And I'll tell you what you do see. You see bubbles forming. And eventually that stops. And the metal is gone. So draw from that what you need to determine what your limiting reagent is. You need to define the rate of the reaction. Now here, that's defined as grams per second. Normally, we do it as concentration per time. Change in concentration over change in time. You need to explain a catalyst. What is a catalyst? What effect does it have on the reaction rate? What effect does a catalyst have on the amount of product? And is a catalyst considered a reactant? And all 4 of these I talked about in the lecture for this particular experiment. So I said what a catalyst was. I said that it has an effect on the reaction rate. What? You should know that. what effect does it have on the amount of product? It doesn't affect that equilibrium position at all, and it is not considered a reactant. Okay, just in case you missed it, it was not considered a reactant, and that's because I use it and it comes back unchanged, so it's not considered a reactant for that. Now, using the kinetic molecular theory, the collision theory that we've been talking about, explain how each of these can increase the reaction rate. And so you're talking about this in theory. So when we talk about temperature, for instance, we expect that these molecules have higher values of movement. So they move more at higher temperature. So if they're moving more, they should collide more. That's how that looks. We need to talk about the effect of temperature, concentration, surface area, catalyst, and the pressure of a gaseous reactant. Now, there is some information about that in the introduction that's here. There's also some in the lecture that I talked about in terms of what that means. If you have any questions, comments, problems on that, please let me know and I'll be happy to walk you through it. And what are the two requirements for a collision in order to form an activated complex? I've actually listed three. I list three all the time. So they have to collide. They have to collide with sufficient energy, and they have to collide with proper orientation. So I would say sufficient energy and proper orientation are the two that I would be looking for there. Because without those things, we can't have that reaction happen successfully. Okay? And that's it. That's your post lab. So that's everything for experiment 9. Now, again, this should not be a big deal. If it is, please let me know. Now, experiment 10 is on Alex. I'm going to do a short video about experiments 10 and 11, probably Wednesday, so that you have some information about what we're looking for, what we're looking at, why we think it's important, why did we do this, why did I make you look at it? So we will talk about that a little bit. It's really not necessary to have a walkthrough for those two videos since they are virtual labs. You have everything that you need. But it is, I think, important to mention them in the context of what you're supposed to be learning from the lecture. So I will talk to you about that part of it. Again, this is everything for experiment 9. So I hope you guys are good. And if you have any questions, please let me know. I'll see you soon.